Thank you. I'd like to thank the organizers for the opportunity to talk here. So my talk today will be based on series of work, mostly done with Freddy Cartreso and Alice Yuan for the past more than 2 years. So actually the first series of work has already been reported by Freddy in Streams 2 years ago. And so I'll also spend more time on more progress on this development of the formulation. And also there's a recent update based on work with my student, Yong Zhang. Okay, so since this is the first talk of this amplitude session, I'd like to give some general remarks. So basically, we all care very much about the S matrix of quantum field theories, and not only because they are needed for colliders. You know, when we consider proton colliders, you need really amplitudes of many gluons, both tree and loop level. But also, I think we think it's very important at fundamental level that this S matrix provide us with some way of seeing more deeper and more profound structures in quantum field theory and also with quantum gravity. So whatever new things happen there, it should already been seen in form of perturbative S matrix, as we will see shortly. So the goal here is really to, from study S matrix, we want to understand more about quantum field theory and gravity. The traditional methods, for example, using Feynman diagrams is not optimal for computing, for example, gluon scattering or graviton scattering. You can see that the number of Feynman diagrams increase very, very fast with number of external legs. And even for 5 gluon scattering process, you get a very, very complicated answer from Feynman diagrams. And the key here is that every Feynman diagram is not gauge invariant. So you carry with you all these redundancies of particles with spin. Well, we do see the final answer is really simple. For example, for this so-called MHV gluon scattering amplitude, this is the one-line formula for them, expressed in terms of the spinor variables, which are actually invented here 30 years ago. So we like to ask, is this just a coincidence of that particular amplitude, or is it a more general feature? And Witten's twisted string theory actually provided a very nice answer 10 years ago. Basically, it says that the simplicity and structures of S matrix can be understood from a worldsheet model. So Witten basically had a worldsheet model for gluon tree amplitudes where he wrote the tree amplitudes in the supersymmetric gauge theory as a string correlator based on a map from the Riemann sphere to a target space as a CP3/4. And the key observation here is that the Park-Taylor formula we see, the simplicity there, is actually reflected in this correlator on the Riemann sphere. So if you remember, we have this spinor variable lambda, and if you write them as a variable expressing a puncture on the sphere, this inhomogeneous coordinate z, 1, this 2 components spinor, the Park-Taylor formula just turns into this simple denominator with a particular ordering given. This is just the Park-Taylor formula. And this is actually follows from, for example, a free fermion correlator on a sphere. This gives you this answer. And Witten's observation is that actually not only the MHV amplitude, the Park-Taylor formula, but also any gluon amplitude, tree amplitudes in 4 dimensions can be written as some image of this Park-Taylor formula to the target space. So basically, you build a map from your Riemann sphere with these punctures to your target space, which has this kinematics of your scattering amplitudes, these spinors. Then all amplitudes can be viewed as a Park-Taylor. It's just some, in the MHV case, it's trivial map. And in the non-MHV case, it's now a polynomial map, which maps this Park-Taylor into something more complicated. So this inspired a lot of developments. Okay, so this is all great. But we like to ask some questions about this twisted string formulation. It's all very special, right? So it's actually for this maximal supersymmetric Yang-Mills theory in 4D. We like to ask if this is a general feature that we can see also without supersymmetry and in arbitrary space-time dimension. Can it be applied to more general theories like gravity, effective field theories, or even the standard model of particle physics? And most importantly, Witten's twisted string theory has problem when you try to go to loop level. So we like to overcome this problem. And this is the topic of this talk, that we try to answer this question. We will provide one answer to this question, which describe any massless particle scattering in any space-time dimension. So basically, you will see that we can provide very compact formulas for arbitrary multiplicity scattering of gluons, gravitons, and other particles in various theories. And more importantly, these are some formulas that are similar to Witten's twisted string formula, but now they actually manifest this important properties of amplitudes in a general setting. For example, this problem with Feynman diagram is that we cannot see gauge invariance manifest. But now in this formalism, everything is completely, you can see them at a very manifest level. And also the Weinberg-Soft theorem and some new soft theorem, and this amplitude relation such as the double copy relation, namely you express gravity amplitude in terms of 2 copy of Yang-Mills and so on, they all become very easy to see. And the very important question is to ask what is the origin of all this? Naturally, we seek origin in string theory. And there are at least 2 ways of understanding this through so-called ambitwisted string or chiral string based on this series of work. You probably heard more from Yutin's talk. That we actually now, I think there's a very good understanding of why. So the very good understanding of why there's this new formulation of general massless scattering. So let me start by introducing you this basic ingredients of the formulation. So basically, the kinematic part of the formulation is very simple. It's encoded in this so-called scattering equations. So these are just n equations that determines this n punctures, locations of n punctures on this Riemann sphere in terms of the kinematics of n massless particles. So you give me n massless momenta. I try to solve these n equations and get the solutions for this n punctures. Okay? So these are very universal and independent of theory. I didn't tell you what theory I'm considering and so on. So this is the backbone of the whole formulation. And it's actually, this equations already appeared in the 70s in the study of dual model in a different context, and also in the so-called Grossman limit of high energy string scattering. The defining feature of this equation is why this set of equations is behind any massless particle scattering, is that they actually probe the factorization property of tree amplitudes, and also later you will see generalized to loop level directly. So basically, if you consider physical singularities of your amplitude, both at tree level and at loop level, I mean the poles of your loop integrands, they actually, through these equations and its loop generalization, they are mapped to boundaries of the modular space of n-puncture Riemann spheres. So whenever you see a physical singularity, you see some singularity of this modular space. And the simplest derivation of this equation is actually through the saddle point approximation, which you take the string theory Koba-Nielsen factor and you take alpha prime to infinity, and you see that these equations are exactly the saddle point equations of the Grossman of the Koba-Nielsen factor. Notice there's an SL2C symmetry of the sphere here. So I put this code derivation here. You will see that because this is weird, right? So we are considering field theory amplitude, which is alpha prime to 0 limit of string amplitude. But we're actually seeing that this general formula that describes alpha prime to infinity limit appearing here. So we'll see some explanation later. So this is a general formulation. It's basically writing any tree level scattering amplitudes in terms of integral over the moduli space, localized by these equations with some something we call the CHY integrand here. So this will be the part that depends on the theory, this CHY integrand. But this measure part is totally universal. And actually, this integral means is really just summing over solutions, because all the integrals are localized. There are n-3 integrals and n-3 delta functions because of the SL2C redundancy. So you actually need to solve all the equations to get all the solutions, and you evaluate your integrand on these solutions and sum over them. Okay, so this actually provides a very different picture than the usual, space-time local interaction picture of scattering. It's basically saying we can view any massless particle scattering through a worldsheet picture, that they are somehow all come from infinity and hit this Riemann sphere on some punctures, and we evaluate some string correlator on that Riemann sphere and calculate the amplitude from there. Okay, all the Feynman diagrams, Lagrangians, and so on are emergent from here. And more concrete is actually summing over this n-3 factorial object. This n-3 because when you solve this equation, you find n-3 factorial solutions. And you're writing your amplitude as n-3 factorial building blocks that we call virtual amplitude here. Okay, so the remaining task will be, given some quantum field theory, we want to find this integrand or this virtual amplitude, such that when we evaluate on them on the solution and take the sum, we get a final answer. Okay, so these are some development I won't have time to go through. For example, the origin, as I mentioned, this is there's this ambitwious string, chiral string. Actually, they both come from this null string, which is the alpha prime to infinity limit of classical string theory. Usually, when we take alpha prime to infinity, we say, okay, let's quantize it. You get the usual Grossman limit of quantum string, where you have infinite tower of massless excitations. You have all these higher spins. But then actually there's an alternative quantization that lead to ambitwious string or chiral string. That's the origin of this whole formalism through the work of these people. And there are also mathematical aspects of how to solve scattering equations or analytically evaluating them. That's a very interesting subject. And then there are some applications and so on of the formulations that I won't go through here. Okay. So let me present you the original CHY formulas that based on the general formulation I just gave. So basically, I try to write any amplitude as this localized integral or summing over a solution of some integrand. And it turns out that given just two very simple ingredients, you can describe these three very fundamental theories in any space-time dimension. The so-called the gravity, the Yang-Mills, and this so-called bi-adjoint phi cube scalar. You can see the Lagrangian and the flavor decomposition here. It's basically the generalization of the usual phi cube theory that now is bi-adjoint under two groups, like UN cross UN prime. So you're using two Park-Taylors, you can build this so-called double partial amplitudes of this scalar theory. And using a Park-Taylor and this what we call the Pfaffian object that encodes the polarization degree of freedom, you can describe n gluon scattering amplitudes in any space-time dimension. So remember, this is a sum of millions of Feynman diagrams together here, right? So also, if you take 2 power of Pfaffian, you generally get the gravity theory, and if you put the polarization tensor to be symmetric and traceless, you get Einstein gravity. Okay. So let me explain to you. This Park-Taylor ingredient is pretty straightforward. It's just from the Park-Taylor formula we talked before. And let me explain you a precise definition of this reduced Pfaffian. It's actually a simple object of this 2n by 2n matrix of these 4 blocks that have this structure. In the first block, you have k dot k. This B block, you have epsilon dot epsilon, and in the C part, you have epsilon dot k. It's an antisymmetric matrix, and then you take its reduced Pfaffian as a basic building block. So actually, the original motivation for writing this down is to mimic the open superstring correlators. So you can show that actually the open superstring correlator on the support of scattering equation simplify to exactly this Pfaffian. And it has very nice properties, and most important one is the gauge invariant. So let's see why this guy is gauge invariant. You look at this matrix, you want to do a gauge transformation, or in the gravity case, it's actually a diffeomorphism transformation because you can do it to your left polarization vector and right polarization vector independently, right? So you can see that by replacing any epsilon by k, 2 columns or 2 rows become identical on the support of scattering equation. The latter comes from this condition that you need this object to vanish. So this is because of the scattering equation. So actually, on every solution of scattering equation, this object, this Pfaffian or this determinant vanishes. So we see that gauge invariance or diffeomorphism is manifest for every building block, every virtual amplitude. Okay, unlike Feynman diagrams. And here also the determinant is just the Pfaffian squared, so it's the closed string correlator. And we see a curious observation here that the CHY integrand for gravity is the 2 copies of CHY integrand for Yang-Mills divided by that of phi cube. And let's see this so-called double copy relation more closely. So the first such double copy relations actually come from the field theory limit of this famous KLT relations, which is originally for the relation between closed string and open string amplitude. And you take the field theory limit, you get the gravity amplitude is actually 2 copy of Yang-Mills amplitude with some function of Mandelstam in between. And this actually can be understood from CHY very easily, that given any theory, not necessarily gravity, just any theory that has a CHY representation of left and right half integrands. So if your CHY integrand can be factorized into 2 parts, you can immediately derive that this amplitude is written as the double copy of 2 sets of color ordered amplitudes with this Mandelstam object in between. And the Mandelstam object is nothing but the inverse of the double partial amplitude I introduced before. So here are these 2 partial amplitudes, left and right, sitting there. So this is now not only applicable to GR equals Yang-Mills squared divided by phi cube, but actually in many more theories, as we will see shortly. Okay, so what about other theories? Let me introduce you. There's some operation that you can do to apply to the old theories to obtain new theories. For example, you can do dimension reduction. From Einstein gravity, if you do dimension reduction, you get Einstein-Maxwell. Graviton coupled to photon to Yang-Mills, you get Yang-Mills with scalars. And these are very simple formulas for them just by doing dimension reduction, where you have this original Pfaffian prime psi now become this Pfaffian prime A and Pfaffian X, which is the kinematic part and the flavor part. Okay? So these are very trivial operations, but there are some very interesting operations to generalize this actually to Einstein-Yang-Mills theory and also Yang-Mills theory coupled to this bi-adjoint scalar theories. I won't list their formulas here, just saying that there's a well-defined operation acting on CHY formulas to get them. And most important, that this is actually exceptional effect field theories that I want to discuss. They are some effective field theories of Goldstone scalars that has some very special property. Namely, if you take one of the momenta of the particle to be soft, it shows this, the amplitude vanishes to some power, this so-called enhanced Adler zero. So actually there are this list of 3 exceptional effective field theory, namely a nonlinear second model with this Pfaffian prime A squared with Park-Taylor, and this Born-Infeld theory, or DBI, bidimension reduction, and also there's a so-called special Galilean theory. So actually, under the soft limit, this series show very nice Adler zero, and they're in some sense unique scalar theories that can have this behavior. And we already see that there are these double copy relations among them, namely Born-Infeld is Yang-Mills crossed with nonlinear second model, and the special Galilean is nonlinear second model squared. So all this is summarized in this roadmap of the theories we discussed. You know, from GR you get Einstein-Maxwell, Einstein-Yang-Mills, and you can go back to Yang-Mills. Same can apply to this Yang-Mills series to go back to phi cube. And then there's this class of theory of Born-Infeld, DBI, nonlinear second model, and special Galilean. So in this direction, you see the double copy relations among them. Okay, and also the soft theorem becomes very manifest in this story. The old Weinberg soft theorem, including their subleading corrections, with some recent work of Schrödinger and so on. This is a very interesting story that becomes manifest from CHY. And also these effective field theories, they show some double soft scalar theories that's very reminiscent of the gauge theory and gravity case. We still don't understand why, but there's this similarity between the two, which will actually reveal you some closed structure of nonlinearly realized symmetry. And also you can go back to 4D, in particular in this DBI Volkov-Akolov theory. You can understand its various double soft theorems from the formulation. So how about loop level? All I've been talking about is tree level, but actually there's a very natural way to go to loop level, which is through Feynman's tree theorem. You can write loop amplitudes from the forward limits of tree amplitudes. Imagine you take n plus 2 particles at tree level, and you take the forward limit of the additional 2 guys. You can actually obtain all the Feynman diagrams at one loop level. However, this is a problematic in general because you run into divergences, so you need regularization. And also you need off-shell momenta for the additional 2 guys because your loop momentums are generally off-shell. So this is the expression. You get this n on-shell guys, and then some off-shell guys. You can view the off-shellness from the higher dimensional component of these 2 guys, and they are in the forward limit because our momentum now is opposite to each other. And then you are trying to sum over the quantum number and polarizations of these two particles that you identify and do the loop integral. This will schematically give you the one-loop Feynman diagrams. So actually, both these problems are solved in CHY because we don't care about what offshore momenta from higher dimension. We just deal with them in any dimension. And also, if you put in the chi amplitude represented by CHY formula, it naturally provides a regularization of these four limit divergences. So actually, you can obtain this one-loop formula for CHY, for CHY formulas for one-loop amplitudes with this one-loop scattering equations. That now you describe one-loop amplitude with n+2 punctures on the Riemann sphere. Okay? So this agrees with ambitwistor results which they obtained originally from this torus picture, that how to go from torus to a Riemann sphere. There's a subtlety related to this representation. Actually, it seems to give you a wrong representation because it differs from the standard representation, but actually they give you the same integrated result. So in some sense, this is a new representation of loop integrands. Let me just show you the formulas. Okay? So you have a one-loop octalar and a one-loop Pfaffian. Of course, now the Pfaffian depends on what internal particle you have. It can be a Pfaffian with scalar loop or gluon loop or fermion loop. They are all very simply obtained from the tree-level Pfaffian with n+2 particles. And now you just plug them in, you get phi cube, Yang-Mills, and gravity, if you have these three combinations. And if you now also include fermions, you can get one-loop CHY formulas for super Yang-Mills and supergravity. Okay? So everything here is very explicit. You can actually get this representation of one-loop amplitudes fairly easily. So also, these properties are actually quite manifest. You can see why one-loop integrands are gauge invariant, satisfy correct soft theorems, and unitarity cuts are just like the factorization of tree-level amplitudes. You can easily see them from a factorization property of your one-loop scattering equation and supersymmetry and so on. But there's still some issue that bothers me, at least, that this gives you a non-standard integral representation, and how to perform loop integrals in this representation is an open question. Okay? So I also wanted to talk about some new works, just 2 slides, that bring us back to 4 dimensions, because this is still the most interesting case, and try to make contact with Witten's twistor string and various twistor string-like formulas in 4 dimensions. So actually, it's probably not emphasized enough, but CHY representation really simplifies a lot in 4D. Because although we see the CHY formulas are generally very compact, but this Pfaffian object and so on, they're actually very, if you expand them, they're still very complicated objects. But all those are basically gone when you go back to 4D. The key here is to notice that unlike in general dimension, in 4D, there's a natural notion of sectors that you're probably familiar from the helicity sectors of 4D amplitudes with gluons and gravity. But this is something, at least a priori, very not related to that. It's just a property of scattering equations. If you reduce the scattering equation to 4D, as we already pointed out in our first paper of all this, they just become the RSV Witten scattering equations in the original Witten twistor string formula. But now it's not a one-to-one correspondence. The equations fall into n-3 sectors, and each sector you have a set of RSV Witten equations. For example, this k equals 2 and k equals n-2 equations just give you linear solutions that's known as MHV or MHV bar solution. But in between, there are also generally complicated scattering equations and solutions. So you can write this summing over solution into summing over sectors and then summing over all the solutions in a given sector, right? And you define this second sum as our amplitudes in a particular k sector. So notice this, I haven't talked about helicity at all. This is just a property of scattering equations in 4D. So you can actually formally write that there's this, every sector you can write a 4D scattering equations with 4D measure, that's the RSV Witten equation, with some 4D integrand. The key point is that this 4D integrand becomes very, very simple. All this complexity of Pfaffian and so on is gone. So this is because the Pfaffian actually is only non-vanishing when the helicity sector coincides with the solution sector. So out of all these sectors, when you want to compute the nk MHV amplitude, you only need to pick the correct sector, so much less than n-3 factorial to evaluate it. And in particular, for effective field theories, you only need the middle sector. So somehow it has a property that it vanishes unless you're in the middle sector. So for example, you can see that this is the 4D integrand. All these Pfaffian are gone. For super Young Mills, it's just a Park-Taylor. For supergravity, is an object that's still like the Pfaffian object, but now it's split into lambda part and lambda tilde part. And then for this DBI-VA theory, is just a determinant prime A. So all the helicity structure, helicity dependence, polarization dependence is as usual going into the measure that has the supersymmetric delta function. And you can easily actually generalize it to more realistic 4D amplitudes, such as amplitudes with quarks and amplitude with Higgs. Actually, this is a recent work with Yong that we discovered we can write down general amplitudes of gluons and pairs of quarks just by modifying the super Yang-Mills fermionic delta function to write down a Jacobian that depends on these quarks. So the Jacobian only depends on the punctures of the quarks, not about the gluons. So you can generally determine this explicit form of this fermion, that J fermion that gives you a new representation of all massless QCD G amplitude. And putting Higgs in is also very interesting because this is very different from usual perspective of viewing the massive particle as coming from higher dimension. This is a Higgs mechanism. So actually you view the Higgs as the massive momenta of the Higgs as the sum of two massless on-shell momenta. And then you write down this formula that express your n gluon and 1 Higgs amplitude in terms of some n+2 puncture on the Riemann sphere integral. And the integrand is simply a Park-Taylor. So again, this is a very simple formula that gives you any tree amplitude with the Higgs and the gluons. Okay, so this actually also opens up a new direction because this Higgs amplitude is at the same time the form factor of a Chase F-square operator with an on-shell state. So from here, we can actually consider if there's a possibility to write down such CHY or connected formulas for general form factors with one off-shell operator, or even for correlators where you have all the operators are off-shell. So this is really how to go off-shell in this CHY representations. Okay, so I'm going to summarize. Basically, I give an overview of this new picture we suggested that tried to describe all the massless particle scattering through these Riemann spheres. And this is like suggests a weak duality between quantum field theory S matrix and the worldsheet models. And they are complementary to Feynman diagrams. For example, we see all this gauge invariance and so on manifest, but they are manifest through these M-3 factorial building blocks. And there are also relations of the theories such as double copy and adding different theories with interaction together. And the loop generalization is a very interesting topic because now we can only do integrands. Can we do integrated amplitudes? And also, what's the natural scope of theories and quantities described by this theory? I think another very important future direction is to consider in this formulation, it's really naturally suggested that S matrix should be viewed as a representation theory of some group, because all this summing over solutions and so on is like expressing some index of a quite complicated group that we still don't know. And I think that will be the end of my talk. Thank you very much. I didn't talk about them, but yes. So in the ambitwister story of this, you can naturally formulate scattering equations and the correlators on higher genuses, and they involve this, on the torus they involve this Jacobi theta function and so on, the usual story. The problem is we don't know how to solve them. So basically, you have to through some residue theorem to rewrite them in terms of the sphere Riemann sphere story with more punctures. So this is the loop approach I talked about, which is equivalent to our 4 limit approach. But in principle, yes, all this higher genus scattering equation should be studied more carefully, I think.